Hello, algebra students. Mr. Laurence here, and you can tell I didn't drive into school today. I rode in on my horse. Ba-bum, boom. Anyway, we're going to talk about exponential growth and decay. This should be a review. We won't spend much time on it, but you are going to see it on the park, so I'm going to refresh your memory about it. This is the equation for exponential growth and decay. Remember that an exponential graph will look something, excuse me, like this, right? That quarter pipe thing we talked about a long time ago. It's not a linear graph, it's exponential. How do I know? Because my variable is exponential. You say, Mr. Lawrence, I see lots of variables. Well, yeah, but trust me. Okay, so here's what's going to happen. P is our principal, not our Mrs. Armentrout. It's the principal. It's the amount that we currently have. Okay? R is the percentage as a decimal. The percent as a decimal. Okay, and it's not okay for you guys to do this anymore. Some of you see, 5%, and you go, hey, that's 0.5. No, it is not. That's 0.5 is 50%. It's a half. This is not a half. You divide by 100. In other words, the decimal point, 5 is here, divide by 100, it moves back 2 places. So 5% as a decimal is 0.05. Or if you have a number like this, 1.875%. As a decimal, boom, boom, 0.01875. Do not round that number. Do not round it. Okay? You can round your answer at the end, but don't round that number. You need to know your percentages and your decimals. And I can tell a lot of you didn't watch that video I put together for Laney over spring break. You know what? It was for you too. Why don't you watch it? It's so simple to work with percentages. All right. Oh, I realize you got better things to do. You got to text your friends. You got to watch SpongeBob. I get it. Okay, don't learn something that's going to help you in your life. No, go text your friends. Yeah, good idea. All right. Anyway, so T is our time in years. Time in years. Okay, very important. Time in years. So if they give you months, you got to convert it to years, right? Okay. Now the one, if you're wondering where the one comes from, the one makes it so that we don't have to add old amounts. For example, maybe you were in 5th grade, 6th grade, and you had $100 invested in the bank at a rate of 10%. Now some of you go, well, that's simple. I got 10% after the first year, so therefore I have $10 plus the original 100, so now I have $110. Now, how much would I have at the end of the second year? Well, 10% of this would be 11. So you go, well, that's simple. I'll just add 11 to it. Okay. So where would it be here? 121. Well, then I get 10% of that for the third year. So I'm taking 10% of this. So then I would need $12.10. And so I know how to add, Mr. Lawrence. At the end of 3 years, I have $133.10. Okay, and how about at the end of 4 years? Well, at the end of 4 years, let's see, 10% of that would be 13 point, losing my place, 13.31, right? Yeah, that should be right. Okay, so I add together, and I've got a 4 and a 6 and a 4 and a 1. So at the end of 4 years of investing, I have $146.41. Well, some of you are so lazy and you say, I'll just do it that way instead of learning the new way. Even though the new way is like 1,000 times faster. Watch this, okay? I invested how much? $100. What rate? 10%. Now, it's an investment. It's gaining, so that's going to be a positive. I'm not going to use the negative. And 10% as a decimal would be 0.10. Okay? For how many years? I don't care if you want to do 2 years, 3 years, 4 years. Let's do them all. Let's do them all. I'm going to leave that as T right now. In fact, yeah, let's do this on a calculator here. Let's see. Okay, it's $100. Okay, what are we making here? 10%. And it's a variable. So I'm going to get a graph of this picture, all right? I'm going to have to change my window. It's going up. Yeah, that's okay there. Let's see. Let's make the Y maximum 100. No, that'd be too small. Let's go 200. And let's make our scale $25. 25. Okay. So there's my graph. Okay, now how much money did I start with? I started with $100, right? So if I put in year 0, you know, when I first start the investment, how much do I have? $100. See it right there? At the end of the first year, T is 1, in this case X is 1, how much do I have? $110. Does that look familiar? It should. At the end of the second year, I have $121. Yeah. End of the third year, I had $131.10. It left the 0 off, but it is still the same number. Those are the same exact numbers that I came up with over here. See, there's $133.10 right there. The fourth year should be $146.41. So let's plug a 4 in there. Boom, $146.41. So you see, it's kind of silly to not do this using the formula. How would I do it? Well, I'm going to take $100. I'm going to multiply it by the quantity of, and then I'm going to raise it to the power of the number of years. So for example, if I wanted to figure out 12 years, I could do that. And there we go. So at the end of 12 years, I would have $313.84 approximately. All right, so this exponential growth and decay formula is pretty powerful. So let's try this one. If you invest $500 at a rate of 7% for 9 years, what is the value of the investment at the end of the 9 years? We'll go ahead and use that equation and figure it out. Pause the video. All right, here comes my solution. 500 times 1 plus 0.07 for 9 years. There you go. Now I'm going to go to my calculator. So I'm going to go with 500 times 1.07. Hey, Mr. Laurence, you didn't put the plus in there. I wonder why not. See if you can tell me. All right. I'm going to have $919.23. Yeah, at the end of 9 years. See how simple that is? All right, let's try one more. It's going to be a real quick video, by the way. Where's it at? There it is. Loserville has been experiencing a population decrease at a rate of 4.5%. Today, by the way, I feel a sneeze coming on, so if I sneeze all of a sudden, I apologize. I can't pause the video. Today, there are 15,000 people living. I'm sorry, I hope I didn't blow your eardrums out. I tried to cover the microphone. Today, there are 15,000 people living in Loserville. If this rate continues, what will the population be in 12 years? Oh, yeah, there should be an S on there. Sorry about that. Okay, so let's just set up our equation. A is going to equal 15,000 and 1 plus 0.045, because I just moved the decimal point back 2 places. That's dividing by 100. And I'm going to raise it to the 12th power. All right, so let's do that. 15. Oh, I have a mistake. Yes, I have a mistake, don't I? Loserville is losing people. So it's not plus, it's minus. Yeah. Good thing I caught that. I didn't want any more emails from Sean. All right, so now I can go to the calculator. 1 minus 0.045 and raise that to the 12th power. And in 12 years, we will have approximately 8,632 people. All right, don't round that up. Even if that was a higher number, it wouldn't make sense to round that up because you wouldn't have that many people. All right, now there's another part to this question. What was the population 7 years ago? Now there's two ways to do this one. I used to teach it one way, and then a student, Ben Krieger was his name, suggested another way to do it. Here's how I would have done it. I would have pretended that the 15,000 was the answer to the problem. I'm going to solve for P, and I would have done this. Okay? And so to get P alone, I would divide both sides by this number. I think Mrs. Clark likes to do it this way. And there's nothing wrong with doing it this way. So I'm going to divide 15,000 by this number here, because these would cancel, leaving me just with the amount, right? The principal. Okay, so let's punch that into the calculator. So I'm going to do 15,000. I'm going to divide that by 1 minus 0.045 for 7 years. Okay, and oops, something's wrong. What did I do? Oh, I must have hit the negative instead of the minus. Sorry about that. All right, there we go. So we would have had about 20,704 people, right? But today I do it differently because Ben Krieger mentioned this. He said, Mr. Laurence, 7 years ago is like going backwards in time. Remember we just kind of talked about that with quadratics? So he said he wants to do it this way. Make the time negative. And it was like, wow, I better go home and check, make sure that works. He's like, I'm getting the same answer. I'm like, okay, I get you, but I just need to go and wrap my brain around it. I went home, I looked at it, and I loved it. I loved it. So it is totally okay for you to do it that way. And let's prove to you that it works here. Let's go 15,000. 1 minus 0.045. Raise that to the negative 7th power. And look at that, we got the same exact number. Same exact number. Now, you should be able to tell me why they work. You should be able to tell me why they work. If you remember what x to the negative second equals, isn't that 1 over x squared? When you move the variable to the denominator, or you move it from the denominator to the numerator, doesn't the exponent change signs, right? So look at this. I've got 15,000 divided by 1 minus 0.045 to the 7th power. If I wanted to move this quantity up, wouldn't that have to become 15,000 times 1 minus 0.045 to the negative 7th power, right? Remember moving our exponents, manipulating them that way? There you go. I don't care which way you do it. Either way works. All right, Mr. Laurence signing off. Have a good night, everybody. Slow down.